It's a great pleasure to have Marcello M.Disconzi from Vanderbilt, who will talk to us about general-relativistic viscous fluids. Take it away.
So thank you, Shadi, for the introduction and the organizers for the invitation. What I'm going to tell today is going to be a series of results that I obtained with several collaborators that are written here. And if you have any questions, feel free to interrupt me at any time, okay? This can be very informal. So I want to tell you about relativistic viscous fluids. But before that, let me start introducing you to a relativistic fluid without viscosity, which means an ideal fluid. And that's described by the relativistic Euler equations written here. So I'm explaining what these symbols mean. So here, T is the energy momentum tensor of an ideal fluid, written here. And J is the baryon current of an ideal fluid, also given by this expression. And in my notation here, rho is the fluid density, or more precisely, the energy density. N is the baryon density. P is the pressure, and the pressure is given as a known function of the density and the baryon density. And which function you choose depends on the nature of the fluid that you are studying. Who is the fluid velocity? Sometimes we call it the force velocity, because just reminding everyone that in relativity, the velocity is a vector field in space-time rather than just a vector field in space. And the velocity has to satisfy this constraint, which says that its norm square has to be equal to -1. G here is the space-time metric. And remember, because it's relativity, that's a Lorentzian metric. So, of course, it's allowed for the norm square to be negative. Now is the covariant derivative. Now, these equations, they are essential in the study of many physical systems. It's textbook material. But what I want to tell you about is that there are important situations where we need a theory of relativistic viscous fluids. So let me give you examples of situations in relativity where we need viscosity. So the first situation is in the study of the quark-gluon plasma. So what is the quark-gluon plasma? The quark-gluon plasma is an exotic state of matter that forms when matter deconfines under extreme temperatures and extreme densities. Just for comparison, the temperatures we're talking about here are several orders of magnitude higher than the temperature of the sun. And these temperatures are actually accomplished, they are achieved in modern day particle colliders. So therefore, studying the quark-gluon plasma provides us with a very good opportunity to understand the properties of matter under extreme conditions. And it also gives us a window into the early universe, because according to modern theories, microseconds after the Big Bang, the universe was filled with matter in the form of the quark-gluon plasma. So the discovery of the quark-gluon plasma was named by the American Physics Society one of the 10 most important discoveries in physics in the first decade of the century, and continues to be a source of many breakthroughs. So it's a very important topic in the physics literature. And through a combination of theory, experiments, simulations, and phenomenology, a coherent picture emerged, showing that the quark-gluon plasma behaves like a relativistic liquid with viscosity. Okay, so here are some plots. What I'm plotting is not very important right now. You can ask me later, but the point is that the solid curves are theoretical curves, and the dots are experimental data. So these are measurements for the quark-gluon plasma, and you see that there is a very good agreement between theory and measurements, but that happens only if we put viscosity. If you try to fit this data with the relativistic Euler equations, the curves are going to be very off. So you need viscosity to study the quark-gluon plasma. Okay, so another important situation where we want to put viscosity is in the study of neutron star mergers. For a long time, it was assumed that you could reasonably describe a neutron star merger with the Einstein-Euler system. But these assumptions, they have been revised recently by Alford, Bovar, Honosky, Redzolla, and Schwenzer. And their results can be understood as follows. So what they did, they estimate the characteristic macroscopic length of the system, which is associated with gradients of the fluid variables, and they did that by running some state-of-the-art numerical simulations of general-relativistic ideal fluids for these mergers. Next, using some macroscopic theory arguments, they obtained an estimate for the microscopic scale of the system. And then once you have the microscopic and the macroscopic scales, you can go ahead and compute something called the Knudsen number, which is the ratio between these two scales. And they found out that the Knudsen number may not be small in some situations. And that implies that viscous contributions are likely to affect the gravitational wave signal. Okay. Now, why is that? Well, that takes a little explaining, but that's coming from kinetic theory. Basically, kinetic theory, this Knudsen number, when it's very small, that means that now you can truncate your gradient expansion to zero order and keep only the ideal part. But if the Knudsen number is not small, you have to introduce these further corrections when you do an expansion, right? And that's the situation here. And the first order correction, they are precisely the viscous contributions. Now, there's another argument in favor of viscosity in neutron star mergers, which was obtained independently by Most, Haber, Harris, Zhang, Alpher, and Noronha. That's a different story, but basically what they did, they studied very carefully the microphysics of these neutron star mergers. And what they found that the remnant settles in a regime described by viscous fluid dynamics. And you're able to compute numerically that this causes a shift in gravitational wave frequency during the ring down phase. So in sum, neutron star collisions are intrinsically viscous, and the estimates that people get from these arguments show that the next generation of gravitational wave detectors is going to have enough sensitivity to actually probe these viscous effects. So this is not just a theoretical thing. We are hoping to see this with actual experiments.
So, Marcello, yes. So the mergers that are currently supposedly detected, these are black hole mergers, not neutron stars, right?
No. People did neutron stars already. Yes,
I mean the gravitational wave detectors.
We do have already from neutron stars as well. Yes.
Also,
yes. There was some years ago. Actually, when we were at the Marcel Grossman meeting, they were talking about this multi-messenger event in a not too distant galaxy where two neutron stars merged and they created a gigantic amount of gold. Actually, that was That's one of the things like why people are very excited about this, because I mean we all love black holes, right? But in a certain sense, neutron star mergers can give us much more information, because what people call multi-messenger astronomy is precisely this combination. Not only you can use gravitational waves, but you can use standard telescopes that look at the electromagnetic radiation, and then you can combine these two different sources. For black holes, you don't have electromagnetic radiation.
Right.
We have only.
Yeah, I understood that. Yeah. So, but then why do you say next generation detectors?
Well, because this viscosity effect is very tiny, so you need to have more sensitivity than the current instruments have.
Mm-hmm.
Does that answer your question?
I see. So currently, these viscous effects are not taken into account.
Not taken account, and if they're there, you're not able to measure them anyway, right? Mm-hmm. Because we don't have enough sensitivity.
Mm-hmm. By the way, since we are just talking detectors, do you have any information about when LISA is going to go into operation?
Oh boy. Okay. I have a colleague in the physics department. She's very involved with this. She told me a few weeks ago that they are behind schedule. That's also surprising, but I think 30 something. I don't quite remember, right? But yeah.
Yeah, I heard 35.
Yeah, but they told me that you're behind schedule, but that's always the case, right? So, but you know, okay. So moving on, okay, so we know that, I hope you convinced that viscosity is important, so the question is how to model it, right? And the starting point is always, again, the energy momentum tensor. So here, rho, u, and p are as before. Pi is just an abbreviation for this quantity, which projects onto the orthogonal to the velocity. So the new quantities compared to the ideal case are what we call the viscous fluxes. So they are the viscous correction to the density, the viscous correction to the pressure, the heat flow, in the viscous shear stress. Okay? Again, the pressure is given by an equation of state, but for simplicity, from the rest of the talk, I'm going to assume that the pressure depends only on rho, and so we're not going to have a baryon density, right? That's going to decouple, just for simplicity. Now, of course, this is just a formal expression. To really define a theory, I have to tell you what these viscous fluxes are, right? I have to specify what these viscous fluxes are. Not surprisingly, you have to make some modeling choices. There are many different choices you can make. But roughly speaking, there are two classes of models that people consider in the literature. There are certain choices that lead to what people call first-order theories. In first-order theories, these viscous fluxes, they are given in terms of the density, the velocity, and their derivatives. So these first-order theories are very much like classical Navier-Stokes, where the shear stress is some expression derivative of the velocity. And I'm going to give examples in the next slide. But that's the basic philosophy. So the equations of motion are going to be, as always, the divergence of the energy momentum tensor equal to 0, possibly coupled to Einstein equations. Now, there's another approach that leads to what are known as second-order theories. And in this other approach, these viscous fluxes, they are not given as some expression in terms of the velocity and density, but they are assumed to be new variables. So the viscous fluxes are new variables to be treated on the same footing as the density and the velocity. So in this case, the equations of motion are going to be, as usual, divergence of the energy momentum tensor equal to 0, possibly coupled to Einstein. But now I have to supplement this by further equations of motion satisfied by these viscous fluxes, because if I'm introducing new variables, I also need more equations of motion. And I'm going to tell you in examples which equations of motion people choose for this. But in a nutshell, in a first-order theory, a viscous flux, like for example, the viscous shear stress, is some known expression of the density, velocity, and their derivatives. And in a second-order theory, the viscous fluxes, like the shear stress, they satisfy their own equation of motion. That's the general philosophy. So what I'm going to do next, I'm going to give concrete examples of these situations. Okay. So the first theory of relativistic viscosity goes back to the 40s and 50s, proposed by Eckert and Lifshitz. These are first-order theories defined as follows. The viscous correction to the density is set to 0, and the viscous shear stress and the viscous correction to the pressure are given by these complicated expressions. Okay, so you have to pay too much attention to these expressions right now. I'm just writing here so you can look at them. I just want to emphasize that these expressions contain two coefficients, which are the coefficients of shear and bulk viscosity. So this is very much like the classical Navier-Stokes equations, where you have shear and bulk. And for simplicity, I'm setting the heat flux equal to 0. You don't have to, but I'm doing this for simplicity. So the question is that where do these expressions come from? They basically are a covariant generalization of the Navier-Stokes equations. And there are some modeling choices that Eckert and Lifshitz did, and these modeling choices were made to enforce entropy production to be non-negative because we want the second law to hold. Okay, so these theories, if you look at them, and again, I don't have time to discuss them in detail, but if you go through this construction, they seem very natural. It's a generalization of the Navier-Stokes equations to relativity, but they actually are very bad because they violate causality. It means that if you study these theories, you see that they allow for faster than light signals, and that's a no in relativity, right? These theories allow this because mathematically what is happening is that in the end, these equations turn out not to be hyperbolic. Okay, so these equations turn out not to be hyperbolic. There are other problems with these theories. They also are unstable, and stability here is just in the sense of mode instability. And this instability and acausality results, they apply not only to these two theories, they actually apply to large class of first-order theories. So the message that you should take away from this slide is that it turns out that it is difficult to construct causal and stable theories of relativistic fluids with viscosity. Okay, so the modeling is not trivial. So it's difficult to enforce causality and stability if you try to put viscosity in your theories. There has been a lot of work addressing these issues.
Okay, so that's one example. Let's move on. Let me give another example of a theory that appears in the literature. That's the Israeli-Stewart theory. That's a second-order theory that goes back to the work of Israeli-Stewart in the 70s, although the modern versions that people actually use, they are due to different groups of authors listed here. So how is this theory defined? So this is a second-order theory. So I have to tell you what the viscous fluxes are in the area equations of motion. The viscous correlation density is chosen to be 0. Then I have the divergence of the energy momentum tensor equal to 0. But as I told you, in secondary theories, the viscous fluxes, like this viscous flux, they are new variables. So I have to postulate the new equations of motion. And the equations of motion are written here. They are complicated. The details are not very important right now for the sake of this talk. I just want to make 2 remarks about these equations. First, they all have the form of relaxation type equations. And the intuition that people use is, if you have viscosity and you start with the system in equilibrium and you perturb the system, viscosity should dissipate energy and cause the system to relax back to equilibrium. So that's why people employ relaxation type equations. There are some coefficients that appear here, which are relaxation time coefficients. Now, in these equations, I'm not writing all the terms. There are some source terms here on the right-hand side that I'm writing symbolically, but in principle, they can depend on all the first-order derivatives of the variables. And because this is the first-order system, all these terms are top-order from a PDE point of view. So what this means is that the Israeli-Stewart equations, they are a highly complex system. They're going to be a large system. How large? Typically, is going to be 26 by 26, 26 equations for 26 unknowns, if you include all the fields, in non-diagonal principal part. So it's a really complicated system to analyze mathematically. Nevertheless, despite it being complicated, this theory has several good properties. The first good property is that stability holds. So that's good. That's better than Eckert and Lifshitz. So if you look at linearization about the global equilibrium, which means you take these equations and you linearize about constant states where the viscous contributions vanish. Those equations, they turn out to be causal. Okay, so the linearization about these special states is causal. That's a good thing. Causality has also been proven in some special cases, like in 1+1 dimensions or in rotational symmetry. And last but not least, this theory has been very successful in applications to the study of the quark-gluon plasma. So if you go back to those numerical simulations that I told you about, the theoretical curves here are produced using numerical simulations of the Israeli-Stewart theory. Okay, so this theory has some good physics on it. In any case, it's a good theory, good for many applications, but again, mathematically, we want to know some basics. Things about this. You want to know if the equations are locally opposed, right? That's a very basic question. And also, you want to know that the theory is causal in 3+1 dimensions without symmetry assumption, the general case, especially because the general case is what actually people use in the numerical simulations. Okay, so that's an important question. Again, let me emphasize that what was known about causality was only for this very special case when you linearize about equilibrium. That's not enough to what the realistic case. And that leads to our first theorem. So the first theorem states that the Israeli-Stewart equations are causal, and the Cauchy problem is locally opposed. However, it's not locally opposed in the way that we usually like. It is not locally opposed. I mean, we didn't prove it's locally opposed in solar space. We don't know, may or may not be, but we were able to prove it's locally opposed in Gevrey spaces. Okay, with some more restrictive class of initial data. However, if you look at a simpler situation where you don't have the viscous fluxes, which are the heat flux or the shear stress, then the equation simplifies significantly, and we are able to prove local opposedness in subordinate spaces. And all these results, they hold with or without coupling twice in equations. Okay. So that's the theorem. Let me say that I'm not going to state my theorems in any technical form. Of course, this is not how, if you look at the paper, that's not how it is stated, right? It's stated in kind of formal mathematical language, but for the sake of this talk, I'm going to state things in an informal manner, which I think is enough to convey the main result. And let me give you just a few ideas of how the proof is carried out. maybe you're thinking, oh, what is the big deal with causality, right? All you have to do is to compute the characteristics of the system, right? Boils down to that, basically, plus a few more arguments. However, remember that the system is very complicated. So if you try to compute the characteristics by brute force, you're going to get nowhere. So what we had to do, we had to develop some calculation techniques which are guided by the underlying geometry of the problem. Basically, we try to frame things in terms of the acoustical metric. Of course, the acoustical metric here is not like the one for ideal fluids, and you have multiple characteristics, but it will be the analog of acoustical metrics in this problem. Right? So this geometric intuition helps us a lot. For local opposedness, we are able to show that the system is weakly hyperbolic. So we derive estimates based on techniques of weakly hyperbolic systems that go back to the celebrated work of Leray and Omiya in the 60s. But because we were able to show only weak hyperbolicity, that's why you need Gervais spaces to avoid loss of derivatives. Okay. But again, in the simplified case where Q and pi are absent, we can close the estimates in Sobolev spaces. Okay. So that's like an idea of how the proofs are carried out.
So Marcello, by weakly hyperbolic means that you have multiplicity?
Yes, you have multiplicity.
So constant multiplicities or variable?
Okay, there are multiple characteristics, but that's not the issue, right? Because we can have multiple characteristics and still be strong hyperbolic, like just compressible wire. So the point is that the characteristic roots, they're repeated, right?
Yeah.
They're repeated, yeah.
Right.
Does that answer your question?
Yes, and also you also have heat flow in here. So there are also characteristics with the speed 0 or
well, okay, so I didn't state so we treat the case without heat flow, right? We treat the case with shear and bulk, but without heat flow. That the case with heat flow, it was too complicated. We still cannot do it.
Okay, okay.
Okay, now as I said, I'm not giving the theorem in the informal statements, but of course there are some assumptions we need. And some of the assumptions are that for the theorem, for the conclusion to hold, we have some assumptions that are some quantitative form, which means that some of the assumptions involve some precise inequalities involving several scalar quantities in the problem. It's not very important right now what all the symbols mean. You just need to know there are certain inequalities that need to be satisfied for the conclusion to follow. Okay, those are sufficient conditions for causality. But we also derive some necessary conditions for that. There are several inequalities. Again, here's an example. It's not very important what all these symbols mean right now, but there are certain inequalities that are necessary for causality, which means if the inequality is violated, causality does not hold, right? Now, these necessary conditions, they are very useful. Why? Because what you can do, once you have these necessary conditions, you can go back to the numerical simulations and you can simply test at each time step if this condition is satisfied or not. And if it's not, that means that your numerical simulation is running without causality, is not causal, right? So that's a very important. These necessary conditions from a practical point of view are actually more important than sufficient conditions. And then some people actually did that. I'm not involved with these works because it's on numerical simulations, which is something that I don't know about. But some different groups, actually, they went back to the numerical simulation of the quark-gluon plasma and tested whether these necessary conditions are satisfied or not. And then they found something quite surprising. They found that up to 30% of the fluid cells can violate causality. They do violate causality. Up to 30% of the fluid cells in these numerical simulations are actually violating causality. Okay. Now that's bad. And of course, you may imagine that might raise questions about the inferences that were made many years ago from these numerical simulations, right? I'm not going to discuss that. I'm not going to tell you if you should still trust the numerical simulations or not. That's a discussion for the physicists to work on this. But I think what this shows is that at least this should serve as a cautionary tale for the kind of risks that people run into if they start running simulations of equations whose mathematical properties are not well understood. Okay, at least it's a cautionary tale, I think. Okay, so all in all, despite some of the very good things about this theory, I want to next move to tell you some of the limitations that Israel Stewart has. Okay, there are some limitations. One is that we don't know if the Israel-Stewart are applicable to the study of viscous effect on neutron star mergers. By this, I mean that we don't know if it is the correct theory, might simply be not the correct model. But also, when you do general relativistic numerical simulations, at least I'm told by people who actually do the simulations, that in general, they want to run their simulations with theories that are locally opposing subglass spaces. Okay, and that's not the case as far as you know for Israel-Stewart yet. Again, we didn't disprove that it's not local opposing subglass space, but we were not able to prove that it is, at least in some particular case. Okay, so maybe again we might have a risk if we start running fully general relativistic simulations with this theory because we don't know if it's locally opposing subglass spaces. There are other situations, even in the case of the quark-gluon plasma, that we don't know if the theory is the correct theory to apply. So let me leave it at that. And of course, we might have to make a reassessment of these numerical simulations in light of this causality violation that I just told you about. That's not something that we should ignore completely. It was shown that the Israel-Stewart theory also has difficulty describing shocks. Now, these are fluid equations. In general, we want to talk about shocks. The underlying point here is simply because these equations are not in conservative form. They're not like in divergence form. So we don't know how to define weak solutions for them. So all in all, the message is that there is enough motivation for alternative theories, despite the successes of the Israel-Stewart. So what I'm going to do now for the rest of the talk, I'm going to move to a different model, which is called the BDNK theory. So this is different than Israel-Stewart. This is a first-order theory, which is the combination of several works by several authors. Okay? So the BDNK theory is defined as follows. So again, we start with the energy momentum tensor, and you define the viscous fluxes by these very ugly expressions. Okay. Now, this is a first-order theory, so notice that all the viscous fluxes are given by some expressions involving the density and the velocity. Okay. Now, of course, the expressions are complicated. This is not the kind of thing that you just wake up one day in the morning and guess. I'm going to tell you later on where it's coming from. So, but first, I want to do the following. Let me first assume that this is given and tell you what we can prove with that, and then I tell you where this is coming from. Okay. Now, you see that there are several terms. Just to compare with the other first-order theory, if you go back to Landau-Lifshitz, you look, for example, at the correction to the viscous correction to the pressure. For Landau-Lifshitz was something very simple, the divergence of U with a certain coefficient. In the BDNK, you still have the same term, but you have all this extra junk. And turns out that all this extra junk that makes the equation very complicated, you actually need to enforce causality. Okay. So as I said, let me first state what we can prove, and then later on I'll tell you where these expressions are coming from.
Marcello, is the energy tensor still divergence free?
Yeah, the equation of motion is still divergence of T mu equal to 0. Okay. For Israel-Stewart, that's still the case, but for Israel-Stewart, you have those extra equations which are not in divergence form, right? But here is only that there are no extra equations.
Okay.
Okay, so here's the next theorem. The BDNK equations are causal and stable. The Cauchy problem is locally opposed and is locally opposed in Sobolev spaces, not only Algebraic spaces, Sobolev spaces. And all these results hold with or without coupling to Einstein equations. Okay, so let me tell you how this is proven very quickly. Again, causality boils down to computing the characteristics. The equations are very complicated. We have to more or less think geometrically. This is similar to what we did before for Israel-Stewart. For stability, we rely on a new theorem that we prove that connects stability to causality. It's a long story, but there's a theorem now connecting stability and causality. And then we proved causality. Then you could use this theorem to establish stability. Let me just point out that this theorem has been recently generalized by GUOSIMP. For local opposedness, what we do, we diagonalize the principal part of the system. And we can do this because you already understood the characteristics. So once you understood the characteristics, you can go ahead and diagonalize the system. But there's a catch. The diagonalization is at the level of symbols, right? So to actually go back to the PD, we have the symbols which involve things like, eigenvalues and so on. So there are some rational expressions. So when you pass back to the PD, you no longer have a PD, you have a pseudo-differential PD. So you have to deal with two differential operators. And because this is a quasi-linear problem, you need to deal with the pseudo-differential calculus for symbols with limited smoothness, which is a bit annoying, a bit technical, but can be done. Okay? And these results, they actually are valid if you include the baryon density, right? I was ignoring this, but I just want to stress this point for this theorem. Okay, so then the question is, okay, so you have this BDNK theory that has all these mathematical properties, but is that just mathematics, or is there some physics, right? We need to connect BDNK with physics. And we can do that. We can show that the entropy production is non-negative. This statement has to be interpreted in its proper context. I can comment more about that later if you want, but that's essentially true. The BDNK theory can actually be derived from kinetic theory, so there's a microscopic foundation for it. And it can also be derived from this thing that physicists like, the holographic principle. Okay, so don't ask me about that. I don't know anything about holography. Sorry, my phone is like, I don't know anything about holography, but I'm just pointing this out. If there's a physicist in the audience, they might like to know that. Now, if you want to really do something quantitative, there's nothing you can do other than run numerical simulations, right? And again, I don't do numerical simulations, but luckily some other people did the simulations. So here are some simulations by Pandya, Most, and Pretorius. So these are simulations for a one-dimensional conformal fluid. And what you see here, the solid curves are Israel-Stewart, and the dots are, sorry, the solid curves are BDNK, and the dots are Israel-Stewart. So they're comparing BDNK with Israel-Stewart. And what they found is that if viscosity is very small, BDNK and Israel-Stewart give basically the same result. Okay, so there is basically no difference between Israel-Stewart and BDNK if viscosity is small. If viscosity is large, the theories give different results. But if viscosity is large, you might as well already be outside the regime where either theory is supposed to be a good description. Okay, so maybe we shouldn't trust either theory in this case. Here's another numerical simulation, again, of a one-dimensional conformal fluid done by Pantelan, B, and Figueras. The story is basically the same. Israel-Stewart and BDNK more or less agree where they are supposed to be valid. They disagree where maybe they don't trust the theories anyway. And they also compare this with microscopic theory. So here's now is a two-dimensional simulation of a conformal fluid by Pandya, Most, and Pretorius. So what they did, they considered the evolution of a Kelvin-Helmholtz unstable initial condition. So here the first column is actually the case without viscosity. So what we have is just the formation of vertices, as you would expect if you have a Kelvin-Helmholtz unstable initial condition. And then when you start increasing viscosity, those are the other columns, basically viscosity shears away these vortices, which is more or less what your intuition would expect that viscosity should be doing. And finally, here's another simulation by Pandya, Most, and Pretorius. This is again a one-dimensional fluid, but now using the equation of state of an ideal gas. And here they study the evolution of heat. And what they do, they start with some heat, some temperature profile that's like a Gaussian. And you see that this kind of Gaussian does what you would expect that should be happening with heat, starts opening up. But because the equations are hyperbolic now, this is different than the heat equation, which would simply open up this Gaussian. At the same time that the Gaussian opens up, it starts forming some wave patterns. And that's due to the fact that these equations are hyperbolic. So you have some wave propagating along this temperature distribution as well. Okay,
okay, let me, before you go on,
yeah.
I have a question here. You say we need to connect with known physics. I agree one should do that, but why do you list the holographic principle as known physics?
Okay, okay, so just, okay, I guess physicists like when things are derived from the holographic principle. I'm honestly agnostic about that. I didn't study this topic. I have no opinion whether holography, is really describing physics or not. But, so if you think that the holography has nothing to do about physics, you can just ignore that statement. If you think it has something to do about physics, you might want to know that these theories can be derived from holography. But if you can ignore that statement and maybe be reassured that you can derive BDNK from kinetic theory. It's the more standard thing. Okay. Okay, so in some BDNK reproduces normal expected physics, is a good thing. The summary is that the BDNK theory has many of the good features of Israel-Stewart, plus a good local oppositeness theory in subordinate spaces, which is lacking for Israel-Stewart. Okay. So now the question is that where is this coming from, right? As I said, you don't wake up one day and just guess those complicated expressions. The big idea behind BDNK is that because causality is such an issue for theories of viscosity, we want to take a philosophy where causality should tell you which terms are allowed or not in your theory, and not the other way around. So one of the problems with Eckert and now Lifshitz is that they make several quote-unquote natural modeling choices, which turn out not to be so natural, but they appear natural, and then only later they investigate causality. And here, what we're going to do is, from the very beginning, think that causality has to be present in each step of your modeling choices. Now, how that's done in practice is a long story. I don't have time to discuss, but goes back to this idea that if you have a non-equilibrium theory, there is always a certain ambiguity in defining what you mean by temperature, density, velocity when you're out of equilibrium. In equilibrium, for the Euler equations, that comes straight from a kinetic theory, what these quantities are, but there's a certain ambiguity when you try to define this out of equilibrium. And so in a nutshell, we want to make the correct choices for what we mean by these quantities out of equilibrium, choices that are compatible with causality. Okay, so I can comment more about this later if you have questions, but that's the basic philosophy. Okay. How much time do I have, Shadi?
Well, you started 5 minutes late, so I think that 8 plus about 20 minutes.
So plenty of time. So okay, I'm going to try to finish maybe 7-8 minutes and have time for discussion and questions. So let me just say that one thing that we like in fluids is to study shock or singularities. For Israel-Stewart, I already told you that it's kind of hard to study. For BDNK, it's too early to say, but there has been already some initial investigations for study of viscous shocks in BDNK by Frey-Stuhler. That's a mathematical paper, and Panda and Pretorius also have some numerical simulation on that. And it looks like BDNK has some advantages over Israel-Stewart for the study of shocks and singularities.
You mean the development of shocks, or
no? Not the development. It's like if you start with
you start with a shock.
Yeah.
Okay.
But regarding the development of shock, that's what I want to tell you about. I'm not going to tell you specific about starting with the shock, but about development of shocks. Okay. And the question is that can singularities form in finite time for Israel-Stewart or BDNK? Okay. So I'm not going to use the word shock because we didn't prove that shocks develop. We proved that some singularity happens. Okay, let me state the theorem, then you see what we do. The theorem says that there exists an open set of smooth initial data for Israel-Stewart, for which the corresponding unique smooth solution to the Cauchy problem break down in finite time. This type of initial data consists of localized perturbation of constant states, but these perturbations are large perturbations. Okay. And before you complain, you might say, well, what do you mean by smooth initial data? Smooth solutions, you only prove for Gevrey spaces. But remember, for the case without shear and heat flux, we were able to get solutions in Sobolev spaces. And once you have the solution in Sobolev spaces with a standard continuation criteria, you can get solutions for smooth data. Okay, so for this case, we do have smooth data. Now, the proof follows a very known strategy. We follow the work of Guo and Shadi, right? That they prove a similar result for the relativistic Euler equations. So we assume that the solution exists for all time, and derive some quantitative precise estimates for the evolution of the viscous correction to the pressure. In our setting, without these fields, the only viscous correction is the pressure. So basically, we follow the argument of Shadi and just did the extra estimates we needed for this viscous flux. And then we derive a contradiction, right? Now, of course, this is proved by contradiction, so it does not reveal the nature of the singularity. So that's why I'm not saying it's a shock, right? But it's some breakdown. But as far as you know, this is the very first breakdown result for Israel-Stewart. So, we think that this opens the door now to try to get some more refined singularity results. Okay, so to conclude, I think it is a very exciting time to study relativistic fluids with viscosity. And here are some further directions. I know that your student, Shadi, couldn't be here today, but if you want to report, I'm always looking for students who want to work on these open problems, right? One question is like local opposite for Israel-Stewart in sublat spaces in the general case. That's an interesting problem. We have this breakdown result, but as I said, it's a proof by contradiction. So we would like to understand the mechanism of breakdown. And you can also try to prove some similar breakdown result for BDNK. That hasn't been done. We can also go in the other direction. Instead of breakdown, we can try to prove existence of global solutions. So for this, there exist some very specific special flows that physicists use. And these are flows, for example, there's something called the Gubser flow. There is also like the Bjorken flow. And in these flows, the equation is reduced to a bunch of ODs, and then you can show that these ODs actually exist for all time. Okay, so these are very simple solutions. And now what you can try to do, you can try to perturb these OD solutions and see if you get some global existence. Now, I talked a lot about neutron stars. Now, of course, if you want to really model a star is something like a free boundary problem. You have some fluid body with vacuum outside, so this is a free boundary problem. And now, even for the case without viscosity, for the relativistic polar equations, the corresponding free boundary problem for the case of a physical vacuum boundary was solved only recently. This is a work that I did with Mihaela Ifrin and Daniel Totaro. And it's a question if you can generalize that to the case with viscosity. So in sum, I think it is an excellent field for people who like to do mathematical physics, right? Who like to do mathematics, but mathematics that's very well grounded in physics, in experiments. And so it is an excellent field of research for collaboration among mathematicians and physicists. And thank you for your attention.
Great.
Let's thank the speaker for very stimulating talk. Gave us a lot of homework to do.